Hello everyone, welcome again in Eng-Man YouTube channel. Right now we are in software playlist and we are going to do MBAL simulation. We will be concentrating on transmissibility. So for all of you reservoir engineers or petroleum engineering students who are concentrating on MBAL simulation, and you know that transmissibility is a thing. So hopefully this video will be useful for us all to learn more or to study more about transmissibility. So for our case, we have two blocks of reservoir separated by a leaky fault. So there will be cross flow between them, and we are going to represent the connectivity or the cross flow with transmissibility. All right. So we are on MBAL window. We go to tool. We select material balance. Okay. We go to another window. We go to options and then reservoir fluid oil tank model. Select multiple tanks. And then PVT model, simple PVT production history. We choose by tank. We are not going to do or to involve any well in our simulation for the time being. Compositional model, none. And then we go to PVT fluid properties. I've prepared my PVT data. You can follow along. Formation GOR 650, oil gravity 40, gas gravity zero point 0.6, and everything else 0. For the sake of simplicity, we are going to input 0 to our water salinity. And then let's say we have laboratory data. So I'm just gonna copy my data and paste the table here. All right. So we have input our PVT laboratory data, and then we will match empirical correlations with this laboratory data. And then in our simulation, the correlation will be applied instead of our laboratory data. We go to match, and then we select everything, and then we press calculation. And then the MBAL do the iteration, the matching, and we have stopped the matching. It means that we have achieved quite good match. And then we want to see the matching results. We go to plot. First, let's see the pressure. So I select Glasso here, the pressure, and then I want to see also our match data, which is our actual data, our laboratory data. Okay, so far so good for pressure, but the main thing should be like bubble point pressure and oil viscosity, right? So let's go again to Glasso and we press bubble point and let's see our main data. A perfect match for our bubble point pressure. Okay, so what about the other parameters like gas oil ratio? Let's see our gas oil ratio. So I'm just gonna remove everything. I want to concentrate on Glasso only, gas oil ratio, and our data. Okay, so it's actually good match except in this region. But for me, practically, it can be used in our simulation. So that's for gas oil ratio. What about oil viscosity? Because it's really important for the flow. Let's see, go to Glasso and build, select oil viscosity. This is the profile for the viscosity. And then let's see our data. Yeah, it's good match or except in this range. The same thing with here. Okay, but for practical purpose, let's see that we will be using our Glasso and Beal correlations. Okay, so we close this one, and then for correlations, we go to Glasso, and for oil viscosity, we go to Beal, right? But if you have your own data and you know that, for example, standing or Lassater or the other correlations will match better with your oil, with your fluid property, then you can select as well. And then you do the matching, right? For the time being, let's select Glasso and Beal, validate. All right. Okay, so we have completed our PVT preparation, and then we go to input for our tank data or our reservoir data. I've prepared my reservoir data. You can follow me. Initial reservoir pressure. Okay, for porosity 0.25, and then connect water saturation. For the sake of an example, let's input 0. Water compressibility, use correlation. Gas cap 0.2. We have gas cap actually here, and original oil in place 240, and then we start January 1980. All right, so far so good. Let's say we don't know that we have water influx or aquifer in our reservoir. Okay, so just select none. Rock compressibility, we will use correlation. Rock compression, just leave it as it is. And then for relative permeability, I have prepared my data, and then I'm just gonna copy paste here in MBAL. Right? And also for my production history, I'm just going to use my prepared data and paste the data here. You can see the plot for our reservoir pressure and cumulative oil production. If you want, you can also plot another parameter like cumulative gas production, cumulative water production, and so on and so forth. And then we can validate. So far, so good. Then we have another tank. So we add our tank here. Okay. And we are going to input data also. 210, the same reservoir temperature, reservoir pressure, the same as well. Okay, because actually they are from the same body of reservoir, and there is fault between them, and the fault is leaky. Okay. Porosity 0.25. Conal water saturation, the same. Gas cap, here we have only zero point 0.1. Original oil in place. Let's say we input this one. And then January 1980. Let's say we don't know that we have any water influx for this reservoir, the second tank. Rock compressibility, also from correlation. Rock compression, leave it as it is. Relative permeability, the same data that we have for our first tank. And for production history, I'm just gonna copy paste my data. All right, so for this tank, we actually have water injection for pressure maintenance. Okay, you can plot and you can see the change of the reservoir pressure. Before water injection, the pressure drops quite fast. And then after 1984, water injection starts in, and then we have pressure increase due to the pressure maintenance coming from water injection. All right. Okay, so far so good. You can actually validate. Done. Okay, so we have right now two reservoirs. And then for the main course of the simulation, we go to history matching. And then history setup, you can see user defined history step size. We can use the default 15 days. And then we go to analytical method. Right now we are in second tank. You can see clearly we haven't achieved any good matching, right? This is the result from the simulation or from the calculation, short calculation by the software. And this is the real data. Okay, you can see this is the increased pressure. And then what about the next tank? Clearly also, it doesn't show any match for the first tank. And if you can see clearly, as I see it is, This pressure trend showed at least two gradients. From the first point to the fourth point, the gradient is quite steep, whereas from the fifth points to the next, it shows gentler slope. So from this data, from this observation, we can say, or we can conclude, maybe there is cross flow that finally supports the pressure for the first tank, and maybe the cross flow coming from second tank, or we don't know, or maybe there is pressure support from an aquifer. All right, and that's the thing that we want to check. That's the thing that we want to simulate. Okay, so first we go again for the second tank because this is the more challenging one, right? So I want to, let's say, I know right now that we have actually aquifer, and then we want to simulate, we want to regress on the aquifer. And for that case, we have to disable the period where we already have water injection because it will make the matching quite difficult, if not impossible. Okay. So if you want to disable the data points, you can just double click and you change the status from on to off. All right. Off and off again. All right. So far, so good. Okay. And then finish. And we add aquifer to the second tank. Okay. We go to Hers and Van Everdingen modified method because it is maybe the most reliable method to represent the aquifer. Okay, so for reservoir thickness, let's input 100. And then for the reservoir radius, this one. And for the outer inner radius ratio, we input 3.7. And then for encroachment angle, 190. And then aquifer permeability, 177. Okay, press done. Let's see history matching again. Okay, let's say we still haven't achieved any good matching and then we need to regression. Okay, we go to regression because we want to do history matching, right? And then first select not to all because we have tank 2 and tank 1 actually here. We want to concentrate on second tank or the tank 2 only. So we can select yes for everything in second tank. But let's say we trust and we are quite confident with our tank porosity as well as our reservoir thickness. So I'm not going to do regression or iteration on these parameters. And then we can start doing the calculation or the regression on these parameters. Hopefully it should be fast. We press calculation and then we wait. Okay, hopefully the iteration will be quite fast and then we can continue our simulation. All right, it stops already. Hopefully we achieve good match. Okay. Oh no, not yet. Not so fast, bro. Okay, actually the previous iteration takes too long. Okay. And then so to make it faster, we can also put boundary both for minimum and maximum prediction. So in this case, I input some minimum values. Hopefully using these values as a boundary, the calculation will be faster. Start again. All right, if it takes too long, you can actually see the regression here or the iteration here. If there is no significant change of the regressed parameters, you can actually stop there and see the matching quality. Okay. Let's say for now, I'm gonna abort or I'm gonna stop the iteration. Okay, confirm. And let's see if we accept all the current fits. Accept. Hopefully it is matched. Yeah, you can see it's good match actually. Okay, so for our current model, we can match quite very well actually with the actual data. Okay, so we have almost done with tank 2. Let's do the same thing with the next tank. Okay, so as I said previously, I think the first point to the fourth point is the same gradient. Okay, whereas the next points have different pressure gradient. Okay, let's do that. We are going to disable the rest of the points. Okay, and we want to concentrate on the first 4 points. Okay, first let's input aquifer first. Okay, let's start from these parameters or this value. Done. And then analytical method. Okay, so the red line shows the trend if we don't have any aquifer, whereas the blue line shows the calculation using the imputed parameters or the imputed value. Okay, and then we go to regression. So we have to say no to all first, and then we want to press yes to only the first tank. Okay, we will leave our second tank behind because we already completed the regression or the iteration for the second tank. Okay, yes, for all parameters in the first tank, but let's say we are quite confident with the reservoir radius, reservoir thickness, and reservoir porosity. Why we did this? Because if we have too many parameters to regress on, then our calculation or our iteration will be too long. Okay, so if you are quite confident with some parameters, then you have to stop or you don't need to regress on that parameter. Okay, let's say we are quite confident with reservoir radius, reservoir thickness, and reservoir porosity, and then you press filter. We will concentrate on these 5 parameters only, and then we go to calculation. Okay, it stops already. We have completed the iteration. Hopefully the match is good. Okay, accept all fits. Done. All right, it's a very good match. Okay, so we have achieved good matching for our first tank and for our second tank. Let's see the other tank. Yes, it's quite good, right? It's satisfying actually. Then we can finish here, and you can also check another method, graphical method. This one is for the method this F cumulative water influx divided by ET versus F. F is total withdrawal from the reservoir. Okay. What about Havlena Ode? Quite good, you can see, right? Quite good matching. And then the second method, good as well. And then this one, all right, it's okay. What about the next tank? This is the second, this is the first tank. Let's see Havlena Ode. No. All right, it's okay. For me, practically, you cannot always rely on graphical method. So if you have achieved good matching with analytical method and for some graphical methods, then we can stop there actually. But for the sake of completeness, let's see the other method. All right, we can accept this. This is actually good, this method. And then Campbell method, no. Oh, it's quite difficult to see with Campbell method. Okay. Let's go again to Havlena Ode and then finish. Let's see first again, analytical method. Okay, there is no change from the graphical method because if you wrongly press something in the graphical method, it will at the same time change your analytical method. Okay, so I'm just going to make sure everything fine with our analytical method. Okay, so far so good. And then we can see energy plot. Now you can see that we have 4 drive mechanisms. We have fluid expansion, the blue area, and then the gas cap expansion because we have gas cap actually here. And then PV or pore volume compressibility, the green one, it should be the weakest drive mechanism. And we have water influx. This is of course for the first tank. And for the next tank, the second tank, yeah, we have this one. Gas cap expansion, PV compressibility, water influx, okay? Please remind that we still unable or make inactive our water injection period, okay? So then we want to activate everything and then, or maybe we can first add transmissibility. This is the entree for our simulation, right? This is the main course because we know or we predict that there will be cross flow between the two reservoirs or between the two segments of the reservoir. So we are going to add transmissibility here and then between tank 1 and tank 2, allow flow from both directions. Okay, press done. All right, so far so good. Okay, from now on, we have to be more careful. We are going to check the analytical method again because finally we will do regression with the transmissibility. Okay, let's see, we need to input 5 first. 5 reservoir barrel per day times centipoise divided by PSI. That's the unit for our transmissibility. And for everything else, we leave it as it is. We leave as default. Okay, press done. Analytical method. All right. Using transmissibility, we still achieve good match. And if we don't have transmissibility, we actually already achieve good match also. This is for the second tank. And for this first tank, also it's quite good. But we need to activate everything right now. All right. Hopefully this is going to be awesome. Yes, we will at the same time do regression for both tanks. Okay, we do the same thing with the second tank. All right, so we go to regression and first, yes to all. So this is the last step, the last stage. This is the boss. Okay, and we cannot regress on all the parameters here because it will take forever. So we select the parameters to regress on strategically. Okay, we don't need to regress on gas cap. Let's say we already we are quite confident with our gas cap ratio. So we make it no. I don't want to regress on reservoir radius. Okay, I'm quite confident with reservoir thickness and porosity as well. And then the same thing with first tank. All right. Okay. And then we can go to filter. Hopefully the calculation will be fast. And then we can go to, and let's say maybe we are quite confident that our transmissibility will be in this range to make the calculation faster, right? And also press calculation. Okay, we can just wait. Hopefully it will be fast. This is the challenge actually if you have transmissibility, especially if you have more than two reservoirs. Okay, so make sure that you have a proper amount of data so that you can be quite confident. Let's say you can make yourself confident with oil in place if you have do the volumetric calculation. And yeah, because we actually need to simulate, or we need to do iteration on aquifer parameters, because we actually don't know about the geometry of the aquifer, the permeability of the aquifer, right? So yeah, it is better if you can be confident with your oil in place, and then you can just concentrate on the aquifer, the parameters of the aquifer, right? All right, if the iteration takes too long, you can make an engineering judgment. You can stop the iteration and you see the current match that you have. Okay, let's say that's the thing that we want to do. So I'm going to abort the iteration, because if not, maybe it will take forever. Okay, so you have this best fit, the so-called best fit, and then let's say we choose accept all fits. Okay, and then let's see the matching. Right, it's actually very good. Okay, let's be careful. If we don't put any transmissibility, then the pressure profile should be like this. It doesn't match, especially at the right end of our data, right? But because we have water influx and transmissibility, we achieve perfect match, right? You can see you can see the blue line match the data points. Satisfaction for the first tank. Lastly, this is the end of our simulation. What about the next tank? All right, this is actually very, very good. If we don't have water influx, we will have red line and it doesn't match. And if we don't put any transmissibility, we will end up on the blue line, on the green line, and it doesn't match. But because we have water influx, water aquifer influx, and transmissibility, and we do the regression, the iteration, and we stop at good matching, then we have these results. All right. So let's conclude everything. In this video, we set up two reservoirs. We know that they are separated by a leaky fault. So there will be cross flow between them, and we will represent that cross flow, that connectivity between the two blocks of reservoir using transmissibility. Okay, you can see transmissibility here. And then we do iteration on both tanks. And then after that, we put transmissibility and then do iteration again to find the transmissibility. So the transmissibility, it's around 1.5. Okay, friends, hopefully this video useful for us all to learn more about transmissibility. And hopefully in the next videos, I will show you more cases like maybe gas reservoir or gas well, or another tool, maybe reservoir allocation, Monte Carlo, right? Decline curve analysis, streamlines. So see you again in the next videos. And if it is useful for you, please don't forget to subscribe, like, and share, and see you in the future. Thank you so much.